design of railway structures. For railway structures, kind of the structure on which the railway is moving. Okay, this is defined as a railway structures, and the structures on which the on top slab or on the top of the structure, if the road vehicle is moving, then it is designed with the ASTO standard. It's basically two versions. For railway, we use AREMA standard, and for road structures, we use ASTO standard. For in American country or other part of the world. Okay, basically in Middle East we use American standard. Okay, now this AREMA has four volume. Actually, AREMA is abbreviation of American Railway Engineering and Maintenance of the Way Association. This kind of railway structures for the AREMA has four volume. Consists of four volume. Volume one is for track. So basically, this is the standard related to the uh, alignment. Okay, design of alignment. Okay, what should be the track, rail, and all those things. Volume two is for structures. This is most important for us to start with. Okay, and volume 3 is for infrastructure and passengers, and volume 4 is for system management. Okay, each volume consists of many chapters like structures. The structure volume is consist of timber structure, concrete structures and foundations, steel structures, then seismic design of railway structures, and structure maintenance and construction. So for Tanzania Lot 6, this chapter is too much important for us because we generally deal with these concrete structures only. Okay, for seismic, basically we need to follow this chapter, but in our DBR, they have used the Euro standard for design of seismic design of structures. So basically, this is not too much important for us right now, but chapter is much more important. Okay, in chapter there are many parts. Okay, like clause, we can say section or clause, not clause actually, section, part or section. So in that, this part one is for material test and construction requirement. Part two is for railway concrete, reinforced concrete design. Much more important for us. Okay, this part two. Then please note this. This will help you. Okay, part two to start with. Okay, this is for basic. Matlab to start with, you have to read all these chapters. Uh, but to start with, this chapter are too much important. Okay, part two, part five. This part 16 is for basically for box culvert or culvert. Okay, specific chapter for culvert they have given, and this part 16 pre-stress concrete. If you have to design pre-stress concrete. Okay, then this elastomeric bearing is given in this chapter, steel structures. Okay, in this bearing portion. Now start with chapter 8. Okay. As I said earlier, there are many part or sections. One is for material test and construction requirement. Let's start with part 2, reinforced concrete design. Okay, reinforced concrete design. In which this general section is given the design methods and what is highway bridges and what to be used for highway bridges. This is what I said earlier, ASTO. Yes, abbreviation of ASTO, American Association of State Highway and Transport Officials. Buildings for this is for bridge protection. This is ship impact and all those things. Superstructure protection. Let's start with loads. Okay. Definitions and 2.2.3 of part 2 of volume chapter 8 of volume 2. Okay, in which point B they have given dead loads. Okay, these are some of the unit densities of dead load of railway structures. Actually not railway structure but railway system. Okay, ballast, concrete, ties, track ties and all those things. But this unit density you have to verify with DBR before starting your design, because the values, whatever values given in DBR, they are the approved from authority engineer, and in the end you have to approve your design from authority engineer. So whatever values given in DBR you have to use this as per the country situation or some special situations. Okay, these all are the values of dead load given here. Now, the most important part is live load. Okay, in live load, they have given one train for train in AREMA. This is basically a Cooper. The name of this train is Cooper. Okay, then 80 stand for the maximum axle load. It is in FES and FES system, and 360 is the both are same maximum axle load of this Cooper train. But this 360 is in MK metric system. This is what we use in our design or kilonewton or meter like this. Okay, सो दिस इज बेसिकली फ्रेट ट्रेन और जो मालगाड़ी बोलते हैं वही जो फ्रेट ट्रेन है उसकी स्पीड ज़्यादातर 160 से ज़्यादा नहीं होती मतलब एक टॉप स्पीड ऑफ दिस फ्रेट ट्रेन इज अराउंड 160 किलोमीटर पर 160 kilometer per hour, and this is the configuration and the spacing axle load all this given here. So basically in which maximum axle load is 360 kilonewton and the spacing between these two axle load is 1.5 meter. Okay, so we apply this live load in our structure by two way. Okay, for a long bridge structure like girder structure and with expansion joint, or in which there is no fill between the bottom of ballast and the top of structures. Okay, like our railway bridges, we use this train as a moving load system. Okay, and for culvert like structure in which there is a fill in between the top of rail and the top of structure, top slab, we have to disperse this load. Okay, and need to apply it as a pressure load. Okay, now let's understand how we have applied in this uh, this is the basic model of underpass. Okay, that we have submitted in the lot 5. Okay, and in which this live load is given as pressure load. Basically this is a structure having fill depth. Okay, so for that what we have to do is we have to convert this axle load into pressure load. How we can convert it? We have to, here it is kilonewton, and the intensity of pressure load is in kilonewton per meter square. Okay, so basically we have to divide this kilonewton divide by area. Okay, matlab whatever the dispersion area is coming. Okay, so basically this axle load divided by dispersion in longitudinal direction and dispersion in transverse direction. Now this is the some slide showing the dispersion in both what is the longitudinal direction and transverse direction. As per the standard, the direction parallel to the track, okay, parallel to the track is known as the longitudinal direction, and perpendicular to the longitudinal direction is known as transverse direction. Okay, this is basically plan view of a segmental curve. Okay, this is the plan view of segmental curve. This bottom dotted line shows the dispersion of track. We will see later. Okay, now basically this is to understand what is longitudinal direction and what is transverse direction. Okay, now if this is in this direction train will move, so this is longitudinal direction, and for dispersion of this load in this longitudinal direction, code specifies that the axial load on structure may be assumed to be uniformly distributed longitudinally for a length of 900 mm plus depth of ballast from the tie plus twice the effective depth of the slab. Okay, and should be less than equal to axial spacing. Okay, so if you consider 360 kilonewton load, then the dispersion of this 360 kilonewton load should not be more than 1.5 meter in this longitudinal direction. Okay, so let's see how we have calculated is. So basically what dispersion along longitudinal direction, whatever written in the code, 0.9 plus depth of ballast plus fill plus 2 times effective depth of slab should be less than equal to axial spacing. So by calculating this way we get this value. Okay, which is just don't focus on this number. This is basically for your understanding. So if we get dispersion in longitudinal direction higher than the axial spacing, we will use 1.52 as a dispersion width. Okay, now then along transverse direction. So basically along transverse direction, code space says this is look what I have told earlier. This is the structure having field depth. What is meant by field depth? The look. This is ballast. This is sleeper. Okay. This is sleeper. This is ballast. Okay. This is a typical railway cross section. Okay. And this is field. This is top slab. Okay. Culvert, and this is top slab. So if you see here, there is a fill between this ballast and this top slab. So we have to disperse the load through the fill. Okay. So this for this kind of structure, we need to apply as a pressure load. And suppose if here there is a no fill, then you have to apply as they have to apply load as a moving load. Kind of influence line diagram by the help of influence line diagram. Okay. So for field up, so for this kind of structures or cross section, what code says that this is for dispersion in transverse direction, okay, or lateral direction. For live load from a single track acting on the top surface of the structure with ballasted track or under the fields shall be assumed to have uniform lateral distribution over the width equal to the length of track pi. So this is basically sleeper plus depth of ballast and the fill below the bottom of tie. So fill below the bottom of tie and limited by the extent of the structure. So this dispersion should not be greater than the width of the structures. Okay, so this is calculated here. So length of tie rod plus depth of ballast plus height of fill should be less than equal to the length of the structure. So we get 3.348 meter, which is less than 9 meters. So it's fine. Okay. So now we will convert this axial load into pressure load by dividing this axial load by this two dimension. Okay. So basically we'll get it the intensity of live load without impact. Now, as you all know, the train load is a dynamic load, but we applied it for this box type culvert or box type structure. We applied it as a pressure load. Okay, a pressure load and static load. So we need to add some additional effect of this dynamic load in the form of impact. Okay, at a form of impact. Okay, so in this code, they have specified what impact load should be taken for this live load. Okay, we are right now we are in the section 2. Okay, they have given this formula for calculating the impact load. This is basically the bridge structure. Okay, this the structure having expansion joint. Okay, the structure having no field. This equation is for bridge structure. For culvert structure, okay, for structures having field depth, they have given the different equation in chapter 16. Okay, basically I know the page numbers, so I have directly moved to this portion. Okay, in part 16, I have told earlier you have to focus on this four chapter, focus on four part 2, part 5, part 16, and part 17 for pre-stress concrete. Okay, in part 16 they have given the equation what impact load should be taken for the structure having field depth. Okay, so they have given in figure 8 of chapter 16 and figure number 5, volume chapter 8 section 16 and figure number 5, design equation in metric units. Okay, so they have given here the equation of impact load. Okay, so you have to take 60% impact when h equal to 0.45 meter. I will show you what is h, and 0% when h equal to 3 meters. So if your field depth is more than 3 meter, then no need to consider the impact. Okay, and you have in between that you have to interpolate between 0 to 60%. Now what is h? Here they have given h. Okay, this is the transverse cross section of a structures. Okay, what I have shown in your ppt. Okay, as h is nothing but the distance between base of rail. If you see here, this is rail. Okay, so distance between base of rail to top of box, this is defined as h. Okay, and The equation is given here. What is impact? Percentage of impact. Okay, 60%. So maximum 60% impact you have to consider for fill light when edge is around 0.45 meter. Okay, so vertical distance. So by this distance, by this height, we calculate the impact load. Okay, and then we add it to the original intensity of live load. Okay, and thus we have applied it as a pressure load in a stat look here. Yeah. One thing that is not to be, we have considered only this maximum axle load for a conservative approach. But for a big structure or girder type structure, we generally use a moving load analysis. So for that, the actual load will be considered. Okay. Now this is for single track only. The structures having single track. In Tanzania Lot 6, we almost all the structures we have is single track, except this at station location or as passing at or intersection or loop. They maybe have there may be chances of having more tracks, but for other than this, there is a single track only. So, but what if we have two tracks? Then how to calculate this pressure intensity? Okay, for two tracks, this longitudinal dispersion will be the same only. Okay, there is no changes in longitudinal dispersion. Okay, but for transverse direction dispersion, there is a little bit change. Okay, suppose a case in which there is a two track and depth of fill is around 3 meter. Okay, approximate 3 meter. So what will happen is the dispersion here, the magenta line is the livelihood dispersion line. Okay, this dispersion will overlap. Okay, so what's this all those things I'm saying is given here. Okay, you need to read it. Okay, all this lateral distribution of livelihood if having multiple tracks, this is all is given here, you have to read it. Okay, but I'm giving just a brief overview of it. Okay. So first, structures having two track or multiple tracks or more tracks. Okay, and when the dispersion is overlapping, then code says the dispersion width should be taken as from point this to this point, which is equal to the center distance between center line of tracks. Okay, plus half the distance of dispersion of first track, these two T's, and half the dispersion of second track. Okay, these two G's. And in this case, we have to take the axle load of two track. Okay, so basically what will change? Here, the 360 will be changed by here. The equation is given. Okay, so 360 will be changed by 720, and the distribution with in lateral direction will be of two tracks. Sorry. Okay, and we have to apply this intensity for two tracks. Now, this is for dispersion. This is a one track or two track. Code also specifies the when there is a multiple track on the structure, what values of livelihood should be taken. Okay, if your structure has two track only, this kind of scenario, this two track, then you have to take the full live load. Okay, for three tracks, full live load on two tracks plus half of the other track. For four tracks, full live load on two tracks, half on the third track, and the 1/4 of the remaining track. Okay. Now this is all about live load. Okay. I'm telling you again. Okay. For bridge type structure in which there is expansion gap, not need to have all type expansion gap. There are also indical structure also, but there is depth of fill is 0 meter. Okay, then you have to use this moving load analysis. So basically you have to use influence line diagram there. In that case, you no need to disperse this live load. Okay, you have to apply as a point load, and structures having fill depth, you have to apply this live load as a pressure load. Okay, now move forward to if you have any question, please ask. Okay, at any point of time, it's fine. Okay, then this centrifugal force, this is basically for curve structure or curvature structures having curvature. Okay, now earth pressure. Okay, So basically we use Rankine earth pressure theory for calculation of earth pressure. Okay. Before applying the earth pressure, you need to verify it, what methodology should be used in the DBR. Okay. Approved DBR. Okay. Now similarly here two scenario is there. Okay. For earth pressure calculation, basically look here. This is modified Cooper EAT in which the load has been reduced. Okay, this is given in DBR. This is for generally for serviceability check requirement. Okay, this is not given in AREMA. This is hypothetical. Okay, hypothesis of live load. This is not important for us right now. Now earth pressure. Basically, we apply earth pressure. Okay, we calculate the earth pressure by earth pressure coefficient by Rankine's theory, but we have to check once in DBR before designing. Okay, so basically what we do is for box type structure we model center to center model. Okay, so at each height matlab at respective height we have to calculate the earth pressure intensity. Okay, this is the basic things what we do in a retaining wall and other earth retaining structures. Okay, now in AREMA two additional clauses given. Okay, one is for culvert. Okay, again chapter 16, this is for concrete box culvert. Okay. Hmm. In dead load, okay, they have given these two clause, point B and point C. Okay, in which they have mentioned the minimum lateral earth pressure coefficient should be taken as 0.33 for culvert, and the maximum lateral pressure coefficient should be taken as 1. This is too much high. This is behave like a fluid. Okay, what we do in fluid, gamma into H. Okay, if you for soil, if you take gamma equal to 1, it is kind of soil water only. Okay, so this is too much high, 1 is too much high. Okay, but code specifies that for design of culvert only, this is for culvert only, this is for culvert only, you have to use k equal to 1. Okay, so for culvert structure this minimum earth pressure coefficient will be 0.33 and you can use 0.271 also. This is also gives a governing value of design action. Okay, and this is the maximum earth coefficient. This will update with 1 for design of culvert structures. Okay, for other than culvert structure, code also specify where it is here in chapter 5. Here it is written that earth pressure force to be applied to the structure shall be determined in accordance with the provision of chapter 5. Yes. Okay, no issue. Chapter 5 by entering the page number, and in chapter number 5 in section 5.3, okay, they give clauses regarding computation of applied forces. Okay, we have to read all those clauses. I'm just highlighting one clause which is too much important for us. Okay, in which they are saying if the wall or abutment is prevented for deflecting freely at its crest. Okay, as in case of rigid frame bridge or some type of U-shaped abutment. This is U abutment with fly return. Okay, or in laterally braced or anchored walls, the computation of backfill pressure should be increased by 25%. Okay, this is important. Okay, so for basically you have to increase this earth pressure intensity by 25%. Okay, this is multiplied by 25%. Okay, so two clauses for culvert we have to use 0.33 and 1. Okay, and in this case you does not need to increase by 25%. Okay, and for other structures except culvert you have to use the normal earth pressure coefficient and increase it by 25%. Okay, and need to apply in our model as a sorry, what's happening? Yes, right, that's a trapezoidal loading. Okay, uh, set episode load. It's nothing but it is state load surcharge only. This is for similarly earth pressure, right? At rest. Okay. Now this live load surcharge. Okay. Surcharge is nothing but simply K into Q. Okay. K will be the whatever value we get here. Okay. By Rankine's theory, you does not need to increase this coefficient by 25% or by 1 for this live load surcharge. Okay. This 25% increase or K equal to 1 is only applicable for the earth pressure calculation only. Okay. So basically you need, this is also written in code. Okay. Chapter 16 in Calvert also. Okay. Let me show you. Where is live load? Okay. So here it is written that in a 16.4.3 live load and point T, they have mentioned that you does not need to increase this earth pressure coefficient by some value for calculation of live load surcharge. Okay. Yes, live load surcharge is nothing but K into Q. So basically whatever the intensity of live load without impact, we will multiply with this coefficient K, we will get the live load surcharge intensity for maximum case and minimum case. Okay. And we will apply it as a aerial or pressure load, rectangle pressure load. Here three cases considered. Okay. Left, right and both side. Just try by yourself why these three case needs to be considered. Okay. And if you have any question, then please ask me. Okay. Get back to me. Okay. I will give you the answer. Okay, this now live load surcharge is completed. Now come to chapter 2. Basically, all the loads related to the structures or bridges is given in chapter number 2. Some specific clauses regarding to culvert is given in chapter number 16. Okay, so for basic loads, we need to jump to chapter 2. Okay, so we have seen this impact load and this centrifugal force in earth pressure, then buoyancy. If required, there is a water table around the structures. It's high, you need to consider buoyancy force. Okay, this wind load is very simple way given here. Okay, if you see other course, wind is very complicated, but here it is written that for 161 wind speed of 160 kilometer per hour, we have to consider 2160 pascal as a wind pressure. Okay, for higher intensity of this wind load, you need to increase this wind pressure. Okay, this wind load is given here, wind load again, wind load on live load also given here. Basically for box type structure, the exposed area to wind is very small. Okay, so generally we does not consider this wind load, but if employers ask for this wind load, then we need to consider it. Okay, because the in this, if you see here, here there will be a backfill behind this wall and this behind the wall. This will embedded in the ground. So only the post part of the structure, this will expose to the wind is only top slab. So generally we neglect it. Okay, but if employer ask to take the wind load, then we have to take it. Okay, this is given in here. Okay, this longitudinal force. This longitudinal force is nothing but the force due to starting or stoppage of train. Okay, this is traction or braking load. The equation for this load is given. Okay, this is for KIPS, this is for kilonewton, and where it should be applied also this is given here 2.5 2.45 meter above the top of rail. So basically we have modeled the structure as a center to center, so we have to add this ballast and fill and all those things, and we need, sorry, here this rail and ballast and fill and half thickness of top slab, then we will get the distance between this application of this braking or traction force to the center of top slab. So basically whatever we get this braking force, okay, it is in kilonewton, so we will apply it as a uniform load. So we will divide it by length of structures. Okay, we will get in kilonewton per meter, and this will be multiplied with distance, okay, height. So basically we will get the moment, uniform moment. So we will apply like this. Okay. Where it is traction, yes, this is braking force. Okay, this is braking force, and this is the corresponding moment because this braking force is applicable at some height, so we need to shift here by this braking force and moment. Okay, similarly traction force, just remember braking force and traction forces are opposite here, but there is a single track, then no need to take two direction. Okay, if the two track is there, so in one track you have to apply braking force like this, and in other track you have to apply braking load like this. This will create some twisting moment also that we will need to take care in design. Okay, then this noising force is nothing but the force uh, will applied by wheel to the track. Okay, transverse force, it is nothing but transverse force applied by this wheel, matlab this wheel of wagon, okay, to the track. It is noising force. Okay, we have to apply it as a point load. Okay, so it is applied, is simple. So we have applied it with noising force. Okay, now moving to here. Okay, longitudinal to the frictions here, earthquake force. Now here in Tanzania lot 5 or in lot 6, we will apply this earthquake force by European standard. Okay, so we have to use it is given in DPR only. Okay, so we have to use this apply this earthquake force as per European standard, but earthquake force is nothing but mass into acceleration. Simple. Earthquake force equal to seismic acceleration into seismic mass. So whatever the seismic mass will be present at the time of earthquake, we have to multiply with the seismic acceleration. So basically we will get the seismic force only. Okay, so same thing is given, and the seismic acceleration you can find out by this equation. We have considered the maximum seismic acceleration, so we have not taken find out the time period, all those things. We have just taken the maximum acceleration value. Okay, if you see the curve, then maximum acceleration value you have taken. Okay, so this maximum acceleration will be multiplied with seismic mass, you will get the inertia force, and the various combination we have to take is the 100% seismic force in x direction and 30% seismic force in y direction, and similarly other scenario. Okay, and need to apply it in the model. Okay, this is 100% in x, if you see here, 100% in x and 30% in y. This application of this earthquake force will be varies as per designer to designer. Okay, it's up to you. You can apply as a nodal load also, it's up to you. Similarly in z direction, okay, we have considering 100% in z and 30% in y. It is also possible that we multiply this in the combination also, but we have applied like this. Okay, now seismic earth pressure. When the earthquake come, we have to use seismic earth pressure. The seismic earth pressure will load need to consider. Okay, in for that we have to the DBR says use Monano-Okabe method for calculation of seismic earth pressure. Okay, so basically this is taken from ASTO appendix 11. Okay, these all are the equation, and we have to consider this active earth pressure and passive earth pressure coefficient. The one important thing is they have mentioned that the point of application of the seismic earth pressure should be at mid height. Okay, so this will only happen if you applied this pressure load, seismic earth pressure load as a rectangle earth pressure. Okay, then here only the point of application will be at the mid height. Okay, in our routine case, point of application will not be the basically it will be a bottom from h by 3. Okay, but for a point of applications to be at mid height, we have to apply it as a rectangle earth pressure. Okay, now come to the sorry this The stream flow pressure, this is for the river bridges, okay, and this is ice pressure. Generally, we does not consider for Tanzania, okay. And then other forces is rig shortening, is shrinkage, temperature creep, all those things, environmental support. But generally, for a box type of structure, we generally does not consider settlements, shrinkage, and all those things. Okay, for sorry, for box type structure, you have to, for all type of structure, you have to consider shrinkage and temperature. But okay, so for temperature, look here, the temperature force, we have to consider it. It is given here the value of temperature, but we have to use this is for America, okay, American US. But for Tanzania, we have to follow DBR basically, okay. So basically, this temperature consists of two components: one for uniform temperature, and the second is the temperature gradient. Okay, this uniform temperature is basically for seasonal change, variation of the temperature. Okay, so basically for winter and summer, this kind of variation. Okay, and temperature gradient is for daily variation because at day sunrise to sunset, what will the change in the temperature? We have to taken care of these two component. Okay, so basically uniform temperature you can apply directly by value. Okay, this value simply, it's not a big task. Simply we have to enter the value. This will be the uniform temperature. Okay, now temperature gradient. Okay, now the load diagram for temperature gradient is like this. Okay, uh, n- linear gradient. Okay, so for that you have to apply like this. Okay, but stat does not have, or many other software does not have facility to apply the load like this. Okay, so what we are doing is we convert this kind of load in this way. Okay, so basically what we can do is we if we convert this kind of load in this way, then what can do is we can convert this in two parts. Okay, so one is for uniform temperature and one for is gradient. Okay, so how we can do that? We can take the force and moment due to this kind of loading diagram to the center of section. Okay, and we take we use such a combination of this gradient of loading temperature. This will create the same force and same moment. Okay, so we use, then we get this combination. Okay, so we apply just like a uniform temperature component and the differential temperature component from top to bottom. This is tricky. Okay, you have to matlab, you have to take care of this component. Okay, sorry. So basically the tentative loading part over here. Okay, then this combination load combination for two limit state. Okay, service for two state service load design is given in table these, and the for load factor design it is given in table 8.2.5. Don't worry, generally this elaboration of this load combination will be given in TPR. Okay, it is difficult for Eurocode, but it is simple for these railway structures. Just a second. Uh, if possible, please try to reach the TBR. We will get much more things. Knowledge will be increased. Okay. Other loads and this load combination. Okay. They have not given here, but in other lot 5 DBR, they have explained the. It is simply given here, not an issue. 1.4 dead load plus 1.4 into 5 by 3 equal to 2.33 per 2.33 live load per implex plus centrifugal force per earth pressure plus buoyancy plus settlement. This way, this is the group number and corresponding combination of load. Okay, explore it, you will get it. If you find any difficulties, ask me, no worries. Okay, then comes to next is material. Okay, this is basically for the material properties, concrete, steel. Okay, what should be the compressive strength? Okay, all those things. Then details of reinforcement, what should be the hook and bends, okay, one minimum diameter, standard hook, okay, this concrete, what should be the minimum cover, all those things, okay, it's given in section 2.6. Then 2.7 is for minimum reinforcement for flexor member, okay, if your member like top slab or bottom slab, we have to check after completion the design of top slab and bottom flexor member. Basically, you need to verify this minimum reinforcement has been given or not, okay. Then distribution of flexor reinforcement in flexor member, this is basically for a girder system, okay. This is for basically for shear reinforcement general requirement, what should be the minimum shear reinforcement, all those things given here, and types of shear reinforcement, spacing of shear reinforcement, those things for then limit of reinforcement for compression member, okay, basically for walls or kind of column, okay. So minimum diameter of bar spacing, all those things is given here, okay. And this clause is important for this kind of color structure. Basically the reinforcement in color structure is quite low compared to the underpass and all the big structures. So basically you make sure you don't forget this clause, okay. After this to check with, which says that we have to apply minimum this much amount of reinforcement to prevent the shrinkage and temperature cracking. Okay, this is secondary crack. This will not affect the strength of the structure, but aesthetic. Okay, for architecture purpose, minimum reinforcement should be like this. Okay, then splices, then development length. Okay, basically there will be one general knot structures in which they will mention all the splices and all those basic matlab detailing criteria, right Tanmay sir?
Yes.
Okay, okay. So in general notes drawing they will mention all these what should be the development for what kind of grades and all those things, okay, so you can directly refer from them, but I insist just go through once these clauses, okay, you will, okay, then this, okay, development length for if you may know that development length for tension bar and compression bar is different, okay, so this is for tension bar, bundle bar, then standard tension, all those. So basically detailing criteria is given here, okay, for welded wire reinforcement, plain wire reinforcement, and what should be the splices, okay, where when we can use this mechanical coupler or all those things given here, splices. Then analysis and design general consideration, this is also important chapter in which the modulus of elasticity, expansion coefficient, and those stiffness, all those things is given here, okay, competition for deflection, effective moment of inertia, okay, for calculation of displacement is given here, long term displacement, bearing basically it is given in chapter 15, okay. Composite concrete flexor members, some criteria, okay, what you see here, sorting T gutter construction, box gutter construction, this is the minimum thickness criteria, okay. Then design method, okay, basically it is like in Indian standard we have working stress design and limit state design, so similarly here they offer service load design, okay, and load factor design, but basically in Tanzania we will use this load factor design, okay. So this is service load design is given in section 2.25 to 2.29, okay, you can read. Then after load factor design, okay, it is given in section 2.30 to 2.39, okay, these are the strength reduction factor. In ULS we reduce the strength of the member by some factor, this is all this factor is given here for shear, flexor, compression with flexor and all those things, okay. Design assumption much more important for design of any structures, okay, in which if you read it you will get to know that the stress plus stress block diagram is rectangle, okay. Basically for Indian, the concrete stress block diagram is like this parabolic plus straight. Okay, so but for in they use this kind of rectangular stress block diagram, Whitney stress block diagram. Okay, this makes this AREMA standard very मतलब user friendly, मतलब kind of मतलब say very easy. Okay, so we will get here what should be the maximum compressive strain in extreme compression fiber, all those things we will hit here. This is from by reading this paragraph point F, you will get to know how to create this kind of stress block diagram, what should be the maximum compressive stress in this fiber. Okay, what should be the depth of this stress block. Okay, all those things is written here. Okay, then the maximum reinforcement for flexor member, basically it is like over reinforced and under reinforced kind of things. Okay, uh 10 15. Okay, this is the equation, basic simple equation for design of a particular section. It is nothing but if you see here, resisting capacity equals to ast fy into lever arm. Okay, basically this is this for rectangular stress block, it is here given as a. Okay, what we use in Indian standard 0.42 xu. Okay, here it is written as a depth of stress block. Okay, all this nomenclature is given in the starting of this section 2. Okay, for how to get the reinforcement, percentage of reinforcement for balance section, and this is for rectangle member. Okay, this is for I section and T section with rectangle section with compression reinforcement. This is the equation. Okay, okay, this is for only flexor member. Now this is for compression member with or without flexor. This is kind of columns type or wall of the culvert. Okay, in this we have to develop PM interaction curve and check whether it is safe or unsafe. Okay, or you need to increase the reinforcement. Okay, this is they have given this clause मतलब assumption or say suggestion to create the PM interaction curve. Okay, you have to read it and interpret it by yourself. Okay, if you found any difficulties, please let me know. This is for biaxial bending. This is for uniaxial bending. This is clause for uniaxial bending. Okay, then slenderness effect in compression member. They have given some criteria. Now shear. Okay, shear for they have given what how to calculate shear stress, and then permissible strain, मतलब capacity of concrete. In excess of capacity of concrete, we have to design shear reinforcement. Okay, then what's shear friction for composites or composite section cast at two different times. Okay, this horizontal shear design for composite concrete flexor member, slab and footing. Okay, this is also important for you. How much reinforcement should be placed for slabs? Okay, top slab and bottom slab. The special provision for brackets and corbel. Okay, this is also important in some cases. This is permissible bearing stress for this is for design check for pedestal. Okay. Now serviceability requirements similarly as we have in Indian standard, crack width and displacement and fatigue. This is here. Okay, this is fatigue limit. This is crack width. This is basically criteria for crack width limited by stress in this member. Okay, this is the permissible stress. Okay, equal to z under root under cubic root DC into A should be less than 0.5 Fy. Basically, this z is corresponding to the limit of crack width. Okay, if you have permissible crack width is 0.3 mm, then you have to use 30 kN per mm. And now if your permissible crack width is 0.2 mm, then you have to use 23 kN per mm. This z value. Okay, this control of displacement. This is some commentaries given here. Okay, this for of this chapter. Now this chapter 5. This is basically for a calculation of earth pressure for retaining walls, apartment and piers. Please scroll through once. Okay. Then chapter 16 is for design of concrete box culvert. This is much important for us for culvert structures. Okay. In which they have mentioned what design load to be considered. Okay. They have uh, suggest us to take only three loads: dead load, live load, and impact load. Okay, all other forces like temperature and this earthquake and the longitudinal forces does not need to be considered for design of color. Basically, these are small structures. Okay, this dead load and all those question is given over. Whatever things we have discussed, they have simply given in the form of equation. This will be, I mean, live load plus this impact load. Okay, so this all those things is given here with equation. Libero. Okay, one important clause is here is regarding the longitudinal reinforcement. This is clause is regarding the minimum longitudinal reinforcement for culvert. Okay, this also varies with the depth of fill. Okay, so just read it. It is much more important. Okay, now then this chapter 17 is also important. Those who are designing the business concrete. Okay, okay, that's all from my side for introduction of AREMA standard.